Everybody, I'm going to start out with an example of what the tau function does. It's a number theoretic function that counts the number of divisors of a natural number. Now, tau at 6 is equal to 4, and because for these small numbers like this, you can just list the divisors 1, 2, 3, and 6 are divisors. Okay, these four numbers, that's where the 4 comes from, are the only divisors of 6. Okay, factors, if you want to call them that. Now, this interesting question here, is there a natural number x such that tau at p squared for any p is always equal to x? Now, this certainly wouldn't be true if it was a real valued function. It would be the identity function. But it turns out the answer is yes to this with a slight caveat. Okay, now let's take a look at a couple of properties of this tau function. In fact, what I'm going to write down next is more or less the definition of a prime number. If p is a prime number, that means it only has two divisors, namely 1 and p. And so t at p is equal to 2. There's two divisors of p, and literally this could be the definition of a prime number. Now, another important thing as far as this proof goes is tau at p raised to the k power, where k is just a positive integer, I suppose, is equal to k plus 1. And that's fairly easy to see if you just list the divisors. The divisors would be 1, p squared all the way up to pk, so you have an extra divisor, namely 1 in there. So the answer would be k plus 1. Okay. Now let's get into this, what we're trying to prove here. We want to know, can you find a constant value x that's always true for all primes squared? Now, this result right here says, we're going to make this assumption. It has to do with the multiplicative nature of tau. This says that p and x have no common factors. Okay? We're going to make that assumption and see if we can live with it. Now, the reason why we make that assumption is that the tau function actually splits. This is what it means for a number theoretic function to be multiplicative. It splits. So So what we get right here is something that follows immediately just from this property right here. We split it, and then p squared, p's a prime, has 3 divisors. Those 3 divisors would be 1p and p squared. Okay, so we've gotten this far. All right, now again, we're trying to get a condition on x that'll help us to actually find x. All right, so all I did is just erase this stuff in the middle, folks, and we get this statement right here. Tau at x has to be x over 3, but since tau returns an integer, that forces x to be a multiple of 3. Okay, so this m would just be a positive integer. We'll say m equals 1, 2, 3, ad infinitum. Okay. So what are we going to do? We're just going to check some cases here, folks. This is the case for m equals 1, right? Yeah, you see right here, x is equal to 3m. So this is the m equals 1 case right here. Now, y'all, 3 is a prime, right? So this would be 2 right here, but that's not equal to 3 over 3, which is 1, right? We just saw what 6 was. Tau of 6 is 4. But that's not equal to 2, right? Okay. Now we get lucky on this next try. T at 3 is 3 squared, so this is 3, right? 3 squared, well, you can just say them 1, 2, 3. There's 3 of the, or excuse me, 1, 3, and 9 are the divisors of 9, right? And that does equal to 9 over 3. So 9 is going to be one of the lucky numbers. There may be others. I'm not saying this is the only one. But 9 fits the bill because this statement is equivalent to the original equality, right? Remember, this is the original, this guy right here equals to x. And then we reach these conclusions rather rapidly right here. And so we get 9, and we get x is equal to 9. Now notice that it wouldn't hold up. This wouldn't hold up. We got to be slightly careful because notice that if p was equal to 3, okay, then this wouldn't be, in other words, if P was equal to 3, you would have 3, 9 equals to 1. So we have to exclude P equals, see there, folks? So this is almost true. It holds for all primes. It may hold for 2. I just don't know the value. Okay, that's another problem. It's probably, you probably could see it right now almost if you wanted to, but this is for all primes P not equal to 3. So yes, it holds almost all the time. Any other prime is going to work right here, folks. Now, again, let's take a look at an example. What if we had tau at 53 is a prime number, right? So we'll write down 53 squared. I think 53 is prime, yes. So this is really kind of empty because it's for any prime. We just proved it, but in any event, now we just said x is equal to 9. So times 9. But notice this would be equal to 3 times 3. Okay, because this is the same as 3 squared here, right? And there is a rule that says you can take each of these exponents and increment them and multiply. Here you can directly see what's going on. But there is a rule, a simple combinatorics truth that says if you take each exponent and increment it and take the product, you also get the divisors. But notice this is equal to 9. Okay? There's our magic condition. Nothing special about 53. Any prime will do other than 3. So, we've answered the question here, ladies and gentlemen, with the slight condition that P can't be equal to 3. And you guys can probably have already figured out what would happen if P was 2. There would be a magic number that's not 9. There's some other magic number. You just got to spend a little bit of time to think about it. But in any event, we're done. Hope you enjoyed the video.